Most of the time, reality behaves itself. You drop something and it falls. You flip a switch and the light comes on. Cause and effect. Simple, predictable, boring. But then you hear about experiments that don't make sense. A particle that seems to know what you're going to do before you decide. A measurement made now that changes what happened 5 minutes ago. Two scientists observing the same event and getting contradictory results, both of them correct. Your first instinct is to dismiss it as theoretical weirdness. Mathematical abstraction that doesn't apply to the real world. Except these aren't thought experiments. They're real results from real laboratories, repeated hundreds of times and verified by independent teams worldwide. And they're still completely inexplicable. Not because we haven't gathered enough data, but because the data refuses to make sense. It contradicts everything we assume about how time flows, how causes lead to effects, and whether reality even exists when nobody's looking. This isn't another video saying quantum mechanics is weird. This is about what happens when the weirdness stops being theoretical and starts threatening the entire foundation of physics. When people hear the word paradox, they usually think of logic puzzles or brain teasers, something strange but ultimately harmless. But in quantum physics, paradoxes aren't just intellectual curiosities. They point to something much deeper, a place where our understanding of reality fundamentally breaks down. In classical physics, the world makes sense. If you throw a ball, it follows a predictable arc. If you measure the temperature of water, you get a number that was already there before you looked. You might not know every detail, every air molecule or thermal fluctuation, but the basic logic holds. The world behaves consistently. That's how Newton's laws worked, and later Einstein's relativity. Everything operated on cause and effect. If something happened, there was a reason. But when scientists began examining things at much smaller scales, atoms, electrons, photons, they started noticing something profoundly strange. The rules didn't just become more complicated, they became fundamentally different. It wasn't that researchers didn't understand all the variables, it was that even with complete information, they couldn't predict specific outcomes. They could only calculate probabilities. An electron might be here or there, spinning this way or that way, and until you actually looked, it genuinely existed in multiple states simultaneously. Not because you lacked knowledge, but because that's how reality worked at that scale. That's where quantum mechanics entered the picture. It gave physicists a framework to handle this bizarre unpredictability. Instead of saying this will happen, quantum mechanics says this might happen with this probability. And remarkably, it works. Quantum theory is one of the most accurate and successful scientific theories ever created. It powers modern electronics, enables lasers and MRI machines, makes GPS satellites function properly. Without quantum mechanics, the technological world as we know it wouldn't exist. Our computers, our phones, our medical equipment, all of it relies on principles that sound absolutely insane when you actually examine them. But here's the uncomfortable truth. Even though quantum mechanics works incredibly well in practice, we still don't really understand what it means. The equations describe what particles do with extraordinary precision, but they don't tell us what those particles actually are or why they behave that way. And when physicists try to figure that out, when they dig beneath the mathematics into the actual meaning, they run directly into paradoxes, situations where different parts of the theory seem to contradict each other, where the implications lead to conclusions that should be impossible. These paradoxes matter profoundly because they're telling us something important. We're missing a piece of the puzzle. It's like owning a phone that works perfectly for calls and texts, but occasionally the screen flashes with symbols you can't decipher. Sure, it still functions, but don't you want to know what those symbols mean? Don't you want to understand what's actually happening inside the device? That's what quantum paradoxes represent. They're glitches in the story. We tell ourselves about how reality operates, cracks in the foundation that suggest the foundation itself might not be as solid as we assumed. One of the biggest issues centers on the concept of measurement. In quantum mechanics, a system can exist in many possible states simultaneously, a situation called superposition. An electron can be spin up and spin down at the same time, occupying multiple positions at once, existing in a cloud of possibilities. But the moment you measure it, you only see one outcome. The electron is suddenly in one place, with one definite spin. That transition from many possibilities to one reality is called wave function collapse, and it's completely unexplained by the theory. That's fine from a practical standpoint. Scientists can work with it, engineers can build technology around it. But philosophically, it's deeply troubling. What exactly counts as a measurement? Does it require a machine? A conscious observer? Does the universe somehow know when it's being watched? The theory doesn't say. That vagueness leads to all sorts of bizarre scenarios. Particles that seem to choose their path only after being observed. Systems whose behaviour depends on whether someone is paying attention. In some cases, the outcome of an experiment appears to depend on decisions made after the event already happened, as if the future is reaching back to influence the past. These aren't just theoretical ideas dreamed up by philosophers. They come from real experiments, conducted in actual laboratories, repeated many times with increasingly sophisticated equipment. And every time, the results make physicists uncomfortable because they challenge our most fundamental assumptions about time, space, and causality. The universe appears to operate according to rules that shouldn't be possible, yet there they are, confirmed again and again in experimental data. Even worse, there's no single interpretation of quantum mechanics that everyone agrees on. The theory itself, the mathematical framework, is solid, but what it actually means is hotly debated. Some physicists believe the wave function is just a tool for calculating probabilities, a useful mathematical fiction that doesn't represent anything real. Others think it represents something genuinely physical, an actual entity existing in some abstract space. Some embrace the many worlds interpretation, suggesting that every quantum measurement causes the universe to split into multiple branches, with all possible outcomes occurring in separate realities. Others believe everything's fundamentally deterministic, and we simply don't have access to hidden variables that would make everything predictable again. And then there are those who think consciousness itself plays a crucial role, that the act of observation by a conscious mind is what collapses the wave function and turns possibilities into concrete reality. The giants of physics felt this discomfort acutely. Richard Feynman, one of the architects of quantum theory, famously said, "I think I can safely say that nobody understands quantum mechanics." Niels Bohr, another founding figure, declared that those who are not shocked when they first come across quantum theory cannot possibly have understood it. Roger Penrose stated bluntly, "Quantum mechanics makes absolutely no sense." Albert Einstein, despite his contributions to quantum theory's early development, remained deeply unsettled by its implications, warning that, if quantum mechanics is correct, it signifies the end of physics as a science. And Erwin Schrödinger, whose wave equation became central to the entire framework, eventually lamented, "I do not like it, and I am sorry I ever had anything to do with it." These weren't cranks or outsiders, criticizing from the margins. These were the people who built quantum mechanics, who developed its mathematics, who saw most clearly what it implied, and they were disturbed by what they'd created. Their unease wasn't about the math being wrong. The equations worked beautifully. Their concern was about what the math was telling them about reality itself. It suggested a universe that operated in ways that violated human intuition so deeply that even brilliant minds struggled to accept it. These disagreements aren't merely academic squabbles about interpretation. They reveal how little we genuinely understand about what's happening at the deepest levels of nature. Quantum paradoxes force scientists to confront that uncomfortable fact head-on. They're like cracks appearing in a wall. You can paint over them, ignore them, work around them. But they're still there, and if you ignore them long enough, you might discover the entire structure is less stable than it appeared. That's precisely why these paradoxes keep physicists awake at night. It's not just that the answers are difficult to find, it's that the questions themselves shake the foundation of how we define reality. What does it mean for something to exist? What is causality? What role does observation play? These sound like philosophical questions, but they're grounded in hard experimental data. The universe is showing us something through these paradoxes, telling us that our current understanding is incomplete or possibly wrong in fundamental ways. Every paradox we encounter is a reminder that we're dealing with a universe that might not operate according to the rules we've assumed. Maybe those rules are incomplete. Maybe we're asking the wrong questions entirely. Maybe reality itself is stranger and more flexible than we ever imagined. These paradoxes are powerful precisely because they can't be easily dismissed. They're not errors or artifacts. They're genuine features of how the quantum world behaves, and they're the universe's way of telling us, you're not done yet. You haven't figured this out. Keep digging. The measurement problem sits at the heart of everything strange about quantum mechanics. Before measurement, quantum systems exist in superposition, in multiple states simultaneously. After measurement, we see only one definite outcome. But what happens in between? What causes that transition? What even counts as a measurement? The theory is silent on these questions, and that silence creates space for paradoxes to flourish. Because if we don't know what measurement is, we can't know when it happens. And if we don't know when it happens, we can't draw a clear line between the quantum world of possibilities and the classical world of definite outcomes. This ambiguity isn't a small technical problem. It's a conceptual crisis at the foundation of our most successful physical theory. And until it's resolved, we'll continue encountering situations where quantum mechanics gives us accurate predictions but completely baffling implications, where the math works but the meaning remains elusive, where we can calculate what will happen but have no idea why it happens that way. That's the landscape we're entering, a world where experiments produce results that shouldn't be possible, where interpretations multiply because no single explanation satisfies everyone, and where the very nature of reality remains an open question. The paradoxes we're about to explore aren't oddities at the margins. They're glimpses into the core mystery of quantum mechanics, the thing that makes it work so well mathematically while remaining so profoundly incomprehensible philosophically. Each paradox is a window into that mystery, showing us a different aspect of how strange the quantum world really is. And together, they paint a picture of a universe far weirder than anything our everyday experience prepares us for. One of the strangest and most deeply unsettling ideas in quantum mechanics is the delayed choice quantum eraser. It's not as famous as Schrödinger's cat or the double-slit experiment, but it should be. Because while those experiments are weird, the quantum eraser is something else entirely. It's the kind of experiment that makes you question whether the past is even real, whether time flows in one direction, and whether anything happens at all until someone decides to look. To understand what's going on, start with something simple. Imagine firing a single photon, a particle of light, through an apparatus where it has two possible paths to travel. You can use mirrors, beam splitters, whatever. The point is, the photon can go one way or the other. Now, if you don't measure which path it took, something bizarre happens. The photon behaves like a wave. It acts as if it travelled both paths simultaneously, and when the two paths recombine, they create an interference pattern. This is the same kind of pattern you see if you drop two stones into a pond and watch the ripples overlap. But if you place a detector to determine which path the photon actually took, the interference pattern disappears completely. The photon now behaves like a particle. It picks one path, goes down that path, and that's it. No wave behaviour, no interference. It's as if the mere act of obtaining information about the photon's journey forces it to commit to a single route, collapsing its wave-like nature into something concrete and localised. That's already strange enough. The idea that observation changes behaviour is a cornerstone of quantum weirdness. But the quantum eraser takes this a step further, and this is where things stop making intuitive sense. Instead of deciding whether to measure the photon's path before it goes through the system, you delay that decision. You let the photon pass through the apparatus, let it hit the detector screen and register its position, and only afterward do you choose whether to keep or erase the which path information. Here's where it gets truly bizarre. If you choose to erase the path information after the photon has already been detected, the interference pattern reappears. Not physically, the photons don't move on the screen, but statistically. When you go back and sort the data based on whether you erased the information or kept it, two distinct patterns emerge. One group shows interference, wave behaviour. The other group shows no interference, particle behaviour. And the only thing determining which pattern you see is a choice you made after the photon already hit the screen. Let that sink in for a moment. The photon's behaviour, whether it acted like a wave or a particle during its journey through the apparatus, seems to depend on something you haven't done yet. A decision that happens later, after the event is supposedly over, appears to reach backward and influence what the photon did earlier. It's not that the screen changes, the individual impacts stay where they are, but the meaning of those impacts, the story they tell about what happened, shifts depending on what you do in the future. This isn't a magic trick or a misunderstanding of statistics. It's a real experiment that's been performed many times with photons electrons and other particles, and every single time the results match the predictions. The presence or absence of which path information, even when that information is obtained or destroyed after the measurement, determines whether the data shows wave-like interference or particle-like behavior. The timeline doesn't seem to matter. What matters is whether the information exists at the end of the process. So how can something that happens now affect something that already happened? Doesn't that break causality? Doesn't that violate one of the most basic rules of physics? That causes come before effects? Well, not exactly. You can't use this setup to send information backward in time. The interference pattern only emerges when you analyze the full dataset and group the results based on your later choices. If you just look at the raw impacts on the screen without sorting them, you don't see any pattern at all. It's only when you apply the filter of your decision that the hidden structure appears. But even with that caveat, the result is deeply disturbing. It suggests that the photon didn't have a definite history until you made your choice. It didn't really go through one slit or both slits. It existed in a kind of limbo, a superposition of possibilities, and your later decision about whether to keep or erase the information determined which version of history became real. Not retroactively in the sense of changing what happened, but in the sense of deciding what it means for something to have happened at all. Some physicists try to explain this by saying the particle doesn't have a definite past until the full experimental context is established. Others say the wave function, the mathematical description of the quantum system, contains all possible histories and only collapses into one when the final measurement is made. And then there are interpretations suggesting that time itself might not work the way we think it does. Maybe the past, present, and future aren't separate stages in a linear sequence. Maybe they're just different perspectives on a single unified structure, where everything that will happen is already entangled with everything that did happen. There's no consensus. What everyone agrees on is that something fundamental about our understanding of time is breaking down here. In the classical world, the one we experience in everyday life, this kind of scenario would be impossible. Imagine shooting a basketball toward a hoop, watching it go in, and then afterward deciding whether you were paying attention when you threw it, and somehow that decision changes whether the shot was good or not. That's the level of absurdity we're dealing with. The quantum eraser doesn't give us a clean answer. It gives us a question we can't escape. If the present can determine what counts as the past, if observation isn't just revealing information, but actively participating in which version of reality gets recorded, then what does that say about the nature of time? Is the past fixed, a completed story we can look back on? Or is it more like a draft that keeps getting edited based on what happens next? And if the past is malleable in this subtle, statistical way, what does that mean for the idea of history itself? This is the kind of experiment that doesn't just challenge physics, it challenges the basic framework we use to organise reality. And it forces us to ask whether time, the thing we use to structure every experience we've ever had, is as fundamental as we think it is, or just another layer of approximation hiding something stranger underneath. In most physics experiments, we take for granted that there's one shared reality. If something happens, it happens for everyone. If a measurement is made, all observers agree on the result. You might have different perspectives, different angles of view, but the underlying facts are the same. A particle is in this state or that state. An event occurred or it didn't. There's an objective truth, and our job as scientists is to uncover it. But the Wigner's friend paradox challenges that assumption at its core. It asks a simple but profoundly unsettling question. What if two observers can look at the same event and disagree about what's real and both be correct? The thought experiment was proposed by physicist Eugene Wigner in 1961, and it's structured like a nested version of Schrödinger's cat. Instead of a cat in a box, imagine a person, Wigner's friend, sealed inside a laboratory. This friend is performing a quantum measurement on a system, let's say a particle in superposition, existing simultaneously in two states like spin up and spin down. When the friend measures the particle, they get a definite result. Maybe they see spin up. From their perspective, the measurement has worked exactly as expected. The superposition has collapsed. The wave function is gone. There's now a concrete, undeniable fact. The particle is spin up. Reality has made its choice. But now consider Wigner himself standing outside the lab. He hasn't looked at the result yet. He hasn't opened the door. He hasn't interacted with his friend or the particle. From his perspective, the entire lab, including his friend and the particle, and the measurement apparatus, is still a quantum system. And quantum systems, as long as they're isolated from the outside world, remain in superposition. So, from Wigner's point of view, the particle hasn't collapsed into one state. It's still in both. And because the friend interacted with the particle, the friend is now entangled with it. That means Wigner's friend is also in superposition, having measured both spin-up and spin, down in different branches of the quantum wave function. This is where the paradox emerges. From inside the lab, Wigner's friend experienced a definite outcome. The particle is spin-up, the measurement is done, reality is settled. But from outside the lab, Wigner sees the whole system, friend included, as unresolved, still hovering in multiple states at once. One perspective says the collapse already happened, the other says it hasn't. And both perspectives are using the same rules, the same quantum mechanics, to describe what's going on. So who's right? For a long time, this was treated as a purely hypothetical problem. You can't actually put a human being into quantum superposition, so the scenario seemed safely abstract, a puzzle for philosophers rather than experimentalists. But in recent years, physicists have found ways to test versions of this setup, using particles, photons, and entangled systems that mimic the roles of Wigner and his friend. In 2019, a paper published in Or, Nature Communications demonstrated that two observers in a controlled quantum experiment could, under the right conditions, record contradictory facts about the same system. Not different interpretations, not measurement errors, actual, physically encoded results that disagreed with each other, and both were valid within their own reference frames. This takes us into genuinely uncomfortable territory. In classical physics, if two people disagree about an observation, at least one of them must be wrong. Maybe they misread the data, maybe their instruments were faulty, but there's always an objective fact underneath, a truth that exists independently of who's looking. Quantum mechanics, at least in scenarios like Wigner's friend, seems to reject that idea. It suggests that reality can be observer-dependent, not just in terms of knowledge or perspective, but in terms of what physically happens. Some interpretations try to resolve this by leaning into the many worlds view, where every quantum measurement causes the universe to branch into parallel realities. In that framework, Wigner's friend collapses the wave function in one branch, and Wigner, observing from outside, exists in a superposition of branches where different outcomes occurred. Both are correct because they're no longer in the same world. They've split off into separate timelines, and each timeline has its own version of the truth. That's logically consistent. But it comes with the baggage of accepting infinite branching universes, most of which we can never access or verify. Other interpretations suggest that the wave function doesn't represent something physical. It's just a tool for calculating probabilities, a map of what we know rather than a description of what exists. In that case, Wigner and his friend simply have different information. The friend updated their knowledge when they made the measurement. Wigner hasn't updated his yet. There's no real contradiction, just a difference in perspective. But this view struggles to explain why the math works so well if the wave function isn't describing something real. And it doesn't fully address the experiments showing that these perspectives can lead to measurably different physical outcomes. Then there's the idea that measurement isn't about collapsing anything. It's about entanglement. When the friend measures the particle, they don't force it into one state. They become correlated with it. From Wigner's perspective, that correlation is just another layer of quantum information. The system has grown larger, more complex, but it hasn't resolved. Only when Wigner himself interacts with the lab does his branch of reality lock in. But this just pushes the problem back a step. At some point, something has to become definite, and we still don't know what that something is or when it happens. What makes Wigner's friend so disturbing is that it exposes a crack in the foundation of science itself. The entire scientific method is built on the assumption that experiments produce objective results, facts that anyone can verify. But if two observers can perform the same experiment and reach different conclusions, both supported by the math, then what does objectivity even mean? Can we still talk about the universe having a state? Or are we each trapped in our own version of events, unable to fully reconcile our experiences? Think about what this implies beyond the lab. If reality is observer-dependent at the quantum level, does that dependence go away when systems get larger? Or is it still there, hidden beneath layers of complexity, quietly shaping what we perceive as a shared world? Maybe every conscious observer is constantly collapsing their own branch of reality, and the reason we all seem to agree is just because our branches are so deeply entangled that the differences average out. Or maybe the contradiction never fully resolves, and we're all living in slightly different versions of the universe, close enough to communicate but never quite inhabiting the same truth. The Wigner's friend paradox doesn't offer an escape hatch, it offers a mirror, and what we see reflected in it is the possibility that the universe doesn't have one story. It has many, and which one you experience depends on where you're standing and what you've measured. That's not just strange, it's a fundamental challenge to the idea that there's a reality out there, independent and objective, waiting to be discovered. Maybe there isn't. Maybe reality is something we participate in creating, one measurement at a time, and the version we see is just one thread in an unimaginably vast web of possibilities, most of which we'll never encounter. And once you accept that, once you let go of the idea that there's a single shared truth, the question becomes, how do you ever know what's real? And more unsettling, how do you know that your reality is the same as anyone else's? Most of us grow up with a simple understanding of how time works. Something happens and then something else follows. You wake up, then you get dressed, then you leave the house. You don't leave before waking. You don't get dressed before deciding to. Time moves forward, one moment after another, in a clear, unbreakable sequence. Cause comes before effect. That's not just intuition. It feels like a law of nature, as fundamental as gravity or the fact that things fall down instead of up. But in quantum mechanics, things aren't so straightforward. The equations that describe how quantum systems evolve, particularly the Schrödinger equation, don't distinguish between forward and backward time. They're time-symmetric. Mathematically, if you filmed a quantum process and played it in reverse, the equations would still work perfectly. There's no built-in arrow pointing from past to future. The math is completely indifferent to which direction time flows. At the quantum level, forward and backward are just labels. The laws themselves don't care. That might sound like a technicality, something interesting for mathematicians, but irrelevant to the real world, except it's not irrelevant. Because if the fundamental laws are time-symmetric, and yet we only ever experience time moving forward, then something else must be creating that directionality. It's not baked into the deepest layer of reality. It's emergent, a feature that appears at larger scales but isn't present in the foundation. And that raises uncomfortable questions. If time doesn't have a direction at the bottom, why does it seem so one-directional to us? And more disturbingly, could there be situations where the usual flow breaks down? This is where retrocausality enters the picture. The idea isn't that you can send messages to your past self or prevent something from happening after it's already occurred. That would violate all kinds of other principles in physics, and nobody's claiming that's possible. Retrocausality is subtler. It suggests that in certain quantum scenarios, the outcome of an event can be influenced by something that happens later. Not by changing the past, but by determining which version of the past becomes real. We've already seen hints of this in the delayed choice quantum eraser. In that experiment, a photon behaves like a wave or a particle, depending on a choice you make after it's already been detected. The photon doesn't retroactively move to a different position. But the pattern it contributes to, the story it tells about how it travelled, depends on a decision made in its future. That's not time travel in the science fiction sense, but it is a situation where the present seems to be reaching back and filling in details about the past. Some physicists take this seriously. They argue that maybe causes don't always precede effects. Maybe the relationship between events is more complicated than we thought. Maybe the universe doesn't unfold in a straight line, from past to future. Maybe it's more like a network where influences can flow in multiple directions, and what we call now is just one node in a much larger web of interconnected moments. One framework that explores this is called the two-state vector formalism. In standard quantum mechanics, you describe a system using a wave function that evolves forward in time, starting from some initial state and moving toward the future. The two-state vector formalism adds a second wave function, one that evolves backward from the future. Together, these two wave functions, one moving forward, one moving backward, define the complete state of the system. The present isn't just shaped by the past, it's also shaped by the future. Both boundary conditions matter. This might sound bizarre, but it's mathematically consistent. And in some cases, it actually makes certain quantum phenomena easier to explain. Instead of imagining the wave function collapsing in a sudden, mysterious jump when a measurement occurs, retrocausal models suggest that what looks like collapse is really just the meeting point of two influences. One coming from the past, one coming from the future. The system doesn't jump, it's smoothly determined by constraints on both ends of the timeline. But this comes with implications that are hard to swallow. If the future can influence the past, even in this subtle, statistical way, then what does that mean for free will? If your choices in the present are already part of the structure connecting past and future, are they really choices? Or are they just inevitable steps in a predetermined path? Some people find this idea liberating, a sign that the universe is more interconnected and elegant than we realized. Others find it deeply unsettling, a suggestion that everything is already written, and we're just playing out a script we can't see. There's also the block universe interpretation, which takes time's symmetry to its logical conclusion. In this view, time doesn't flow at all. Past, present, and future all exist simultaneously as part of a single, unchanging four-dimensional structure. You're not moving through time. You're a static pattern stretched across the timeline, and consciousness is just the experience of traversing that pattern, moment by moment. Your entire life, from birth to death, already exists as a complete object in space-time. You're just becoming aware of it piece by piece. This resolves a lot of the weirdness around retrocausality, because there's no before or after in any absolute sense. Everything just is. Causes and effects are labels we apply based on our subjective experience of moving through the block. But from the universe's perspective, they're all equally real and equally present. That's philosophically tidy, but it's also disturbing. It means nothing ever changes. Everything that will happen has already happened, in a sense. You're not creating the future, you're discovering it. Not all physicists accept retrocausality or the block universe. Many prefer interpretations where time remains one-directional, where cause and effect stay in their traditional order, and where the strangeness of quantum mechanics is explained in other ways. But the fact that retrocausality is even a viable option, that the math allows it and some experiments seem to support it, tells us something important. Our intuitive understanding of time, the one we rely on every moment of every day, might not be how time actually works at the deepest level. What makes this especially challenging is that we have no direct experience of retrocausality. We never feel the future influencing the past. We never see effects before causes. And yet, the equations say it's possible. The experiments hint at it. The interpretations leave room for it. That gap between what we experience and what the theory suggests is one of the most profound disconnects in all of physics. And it raises a question that goes beyond science. If time isn't the simple, forward-flowing river we think it is, if the future can shape the past in ways we can't perceive, then what does that mean for how we understand ourselves? We build our entire sense of identity on memory, on the idea that the past is fixed and the future is open. But if the past isn't fully determined until the future happens, then maybe identity itself is more fluid than we thought. Maybe who you are isn't just a product of where you've been. Maybe it's also a product of where you're going, and you won't know which until you get there. One of the most perplexing phenomena in quantum mechanics is how two systems, particles, detectors, or even observers, can coordinate perfectly without ever exchanging information. No signals, no communication, no possible way to share data. And yet, when you check their results, they align in ways that should be impossible. Not occasionally. Every single time. This eerie synchronization is often called quantum pseudo-telepathy, and it's one of the clearest signs that something about our understanding of space, separation, and independence is fundamentally wrong. Let's start with a simple scenario. Imagine a game. You and a friend are placed in separate rooms with no way to communicate. No phones, no signals, no hidden messages. Each of you will be asked a random question, and you have to answer either yes or no. The questions are chosen from a fixed set, but you don't know which one you'll get until the moment it's asked. Here's the challenge. Your answers have to satisfy a certain pattern. If your answers match the pattern, you both win. If they don't, you lose. In a normal, classical world, the best strategy is to agree on a plan beforehand. You could memorize a chart of questions and responses, trying to cover as many possibilities as you can. You'll improve your chances, but you won't win every time. There will always be combinations where your prearranged strategy fails because you can't predict every possible pairing of questions. Without real-time communication, there's a hard limit on how well you can do. The math proves it. But now imagine you and your friend each have one half of an entangled pair of particles. These particles were created together in a specific quantum state, and even though they're now separated, potentially by vast distances, they remain connected. Not by signals, but by a deeper kind of correlation that doesn't require space or time to mediate it. When you receive your question, you perform a measurement on your particle. Your friend does the same with theirs. You still don't communicate. You still don't know what the other person is doing, but when the results are compared afterward, they line up in a way that violates the classical limits. You win rounds that should be statistically impossible to win. This has been tested in real experiments, and the results are undeniable. Players using entangled quantum systems can succeed at coordination games with win rates that no classical strategy could ever achieve. The name pseudo-telepathy comes from this illusion. It looks like telepathy. It feels like the two players are reading each other's minds, working together invisibly. But it's not telepathy. There's no information being transmitted. Nothing is travelling between the two locations. The entangled particles are simply correlated in a way that classical logic can't explain. One famous example is the CHSH game, named after the physicist who formalised it. In this setup, two players each receive one of two possible questions and must give one of two possible answers. There's a specific scoring rule that determines whether they win, based on the combination of questions and answers. Classically, the best strategy wins about 75% of the time, but with entangled particles, players can win about 85% of the time. That 10% gap might not sound like much, but mathematically, it represents a fundamental violation of what should be possible in a local, realistic universe. Another well-known example is the Magic Square game. It's a logic puzzle where two players must fill out a grid with ones and negative ones, following certain rules about rows and columns. In the classical version, there's no way to satisfy all the constraints simultaneously. The game is rigged. You can't win every round, but if the players share entangled quantum states and perform measurements based on the questions they're asked, they can win every single time. The quantum correlations allow them to do something that classical logic says is impossible. So what's actually happening here? At the heart of quantum pseudo-telepathy is entanglement. When two particles are entangled, they're described by a single quantum state. They're not two separate objects with separate properties. They're part of one unified system. Even if you move them light years apart, that connection persists. Measure one and you instantly know something about the other, not because a signal was sent, but because they were never truly independent to begin with. Einstein famously called this spooky action at a distance, and he hated it. He believed it meant quantum mechanics was incomplete, that there had to be hidden variables, some deeper layer of reality we hadn't discovered yet that would explain the correlations without requiring this bizarre non-local connection. But decades of experiments, especially tests of Bell's inequality, have proven that Einstein was wrong. There are no hidden variables. The correlations are real, and they're stronger than anything classical physics allows. What quantum pseudo-telepathy reveals is that the universe is non-local in a deep and unavoidable way. Information doesn't need to travel through space to connect distant systems. Or more accurately, the systems aren't really distant in the way we think. They're entangled, which means they're part of a single entity that extends across space without being limited by it. Distance, in the quantum world, is almost a superficial concept. It's how things look from the outside, but it's not how they're actually connected underneath. This forces us to question some very basic assumptions. Is the universe really made of separate, independent parts? Or is separateness just an illusion? A convenient approximation that works at human scales but breaks down when you look closely. If two particles on opposite sides of the galaxy can remain instantaneously correlated, what does that say about the nature of space itself? Maybe space isn't fundamental. Maybe it's emergent, a structure that appears at large scales but isn't present in the quantum foundation. Some physicists interpret this as evidence that reality is fundamentally holistic. There are no truly isolated systems. Everything is connected to everything else in ways we don't fully understand. Others suggest it means we need to rethink what we mean by real. Maybe particles don't have definite properties until they're measured. Maybe the correlations we see in entanglement aren't because the particles are coordinating, but because the act of measurement creates the results, and those results are constrained by the shared quantum state. Either way, quantum pseudo-telepathy is not a trick. It's not a loophole. It's a direct consequence of how quantum mechanics works, and it's been verified in countless experiments. Two people really can act in perfect synchronization without exchanging any information, simply by measuring entangled particles in the right way. It defies our intuition about how communication works, about how space separates things, and about what it means for objects to be independent. And the implications go far beyond games. If quantum systems can coordinate without signals, what else might be connected in ways we can't detect? How much of what we think of as separate, isolated, independent, is actually part of a vast web of quantum correlations we're only beginning to glimpse? The universe might not be a collection of distinct objects. It might be a single unified system that only looks fragmented from our limited perspective. And if that's true, then the boundaries we draw between things, between ourselves and the world, between past and future, between here and there might all be illusions. Useful, necessary illusions for navigating reality, but illusions nonetheless. There's a quantum experiment that sounds so absurd, it feels like it was designed to mock our intuition. Imagine watching a cat walk through a hallway, but instead of seeing the whole cat move together, you see the body go one direction and the grin float off in another. The grin detaches from the face and drifts away on its own, independent of the cat. That image, straight out of Alice in Wonderland, is the inspiration behind what's called the quantum Cheshire cat. And it's not just a metaphor, it's a real experiment with real particles that appears to separate a particle from one of its fundamental properties. To understand why this is so disturbing, think about what we normally mean when we talk about an object. In classical physics, an object and its properties are inseparable. If you move a spinning top from one table to another, the spin goes with it. You don't expect the spin to stay behind on the first table while the top itself moves to the second. The object and its features are bound together, they're one thing. But in quantum mechanics, that assumption starts to fall apart. In the quantum Cheshire cat experiment, scientists use neutrons, subatomic particles that have both a position and a property called spin. Spin isn't actual rotation like a top. It's an intrinsic quantum property, a kind of internal orientation that affects how the neutron interacts with magnetic fields and other particles. It's fundamental to what a neutron is. You can't have a neutron without spin, or so you'd think. The experiment uses a device called an interferometer, which splits the neutron's path into two possible routes. The neutron is placed in a superposition, meaning it doesn't take just one path. It exists in both paths simultaneously until a measurement is made. So far, this is standard quantum behavior. Superposition is weird, but it's not new. But here's where the experiment gets strange. Scientists arrange the setup so they can measure the neutron's position in one arm of the interferometer and its spin in the other arm. What they find is that the neutron behaves as if it's travelling down one path while its spin is detected in the other path. It's as though the particle went left, but its spin went right. The neutron and its spin, two things that should be inseparable, appear to exist in different locations at the same time. That doesn't just violate intuition, it violates what we mean by an object. How can you separate a particle from one of its defining characteristics? It's like saying you found the heat of a flame in one room and the flame itself in another. It shouldn't make sense. And yet, the measurements are clear. This isn't a mistake or an equipment error. The results come from a technique called weak measurement, a method in quantum physics where you gather information about a system without fully collapsing its quantum state. Instead of forcing the particle to commit to a definite value, weak measurements give you a soft statistical hint of what's happening without destroying the superposition entirely. When you collect enough of these weak measurements, a strange picture emerges. The neutron went this way, but its spin went that way. This is what scientists call a paradox. Not because the math doesn't work, but because the result contradicts our most basic assumptions about physical reality. If a particle's properties can be peeled apart and sent in different directions, then what is a particle? Is it a physical thing travelling through space, or is it just a bundle of quantum properties that can drift apart and recombine? Are properties like spin intrinsic to the particle, or are they more like labels that can move independently? Some interpretations say this is just a measurement artifact, that nothing is really splitting. The properties don't literally separate. It just looks that way because of how we interact with the quantum system, because of the probabilities involved and the way information gets encoded in weak measurements. According to this view, the neutron and its spin are always together. We're just seeing a statistical illusion created by the measurement process. But other physicists take the result more seriously. They argue that the experiment shows quantum systems don't have fixed identities the way classical objects do. A particle isn't a little solid thing with traits like position and spin glued to it. It's a cloud of possibilities, a collection of potential properties, and those possibilities can evolve separately under the right conditions. The quantum Cheshire cat suggests that properties aren't bound to objects in any fundamental way. They're features of the quantum state, and the quantum state can be manipulated in ways that separate those features. If that's true, it has profound implications. It means we need to rethink what we mean by a particle, by an object, by a thing. Maybe particles aren't things at all. Maybe they're patterns, processes, events that only take on the appearance of solid objects when we observe them in certain ways. And if properties can be separated from particles, what else can be separated? Can you split charge from mass? Energy from momentum? Can you have existence without location? The quantum Cheshire cat also connects to a broader issue in quantum mechanics, the role of measurement. If what you observe depends on how and where you look, then reality becomes a kind of interactive process. Objects don't just sit there with fixed properties waiting to be discovered. They take on meaning through measurement, through interaction, through the questions we ask. The neutron doesn't carry its spin around like a permanent feature. The spin emerges based on the context, the setup, the way the system is probed. This echoes something we've seen in other paradoxes, like Wigner's friend. Reality isn't a static thing. It's constructed through observation. The quantum Cheshire cat is one more piece of evidence that the universe doesn't exist in a definite state until something measures it. And when you do measure it, you're not just revealing what was already there, you're participating in creating the result. So if you ever thought quantum mechanics couldn't get any stranger, remember there's an experiment where a particle's property wandered off on its own. The grin without the cat. And the disturbing part isn't that it's a metaphor. It's that the math and the measurements say it's real. There's one quantum thought experiment that goes beyond particles and mathematics and ventures into deeply personal territory. It's not about photons or electrons, it's about you, your consciousness, your survival, and the unsettling possibility that from your subjective point of view, you might never actually experience dying. It's called the quantum suicide thought experiment, and it's rooted in one of the more extreme interpretations of quantum mechanics, the many worlds interpretation. The many worlds idea is straightforward but mind-bending. Every time a quantum event occurs, every time a particle could go one way or another, the universe doesn't choose. It splits. Both outcomes happen, but in separate branches of reality. So instead of collapsing the wave function into a single result, reality branches into all possible versions. You just happen to be experiencing one of them, one thread in an infinitely expanding web of parallel worlds. Now here's the twist. Imagine a setup involving a quantum trigger, something that produces one of two outcomes with exact probability, based on, say, the spin of a particle. For instance, a device that fires a lethal projectile 50% of the time, depending on a quantum measurement. You sit in a sealed room where no one outside can see what's happening, and you press the button. In half the branches of reality, the device fires and you die. In the other half, it doesn't fire and you survive. But here's the key. From your perspective, from the inside of your own conscious experience, you can only ever find yourself in the branch where you survive. You press the button, the universe splits. In one branch, you're dead, but you're not there to experience that branch. Your stream of consciousness, your subjective awareness, only continues in the branch where you survived. So you press the button again. Another split. Again, in half the worlds you die, but you only experience the ones where you don't. No matter how many times you repeat this, no matter how astronomically unlikely it becomes, there's always at least one branch where you're still alive. And from your first-person perspective, that's the only branch you'll ever know. This leads to the concept of quantum immortality. The idea that your conscious experience can only ever continue in the universes where you survive, no matter how improbable those outcomes become. To be absolutely clear, this isn't a claim that you can live forever in any objective sense. If someone watches you from outside the sealed room, they'll see you die in about half the experiments, just as probability predicts. But from your internal, subjective viewpoint, you never reach an end point. You only ever wake up in the versions of reality where your awareness persists. That's where the paradox lives, not in the physics itself, but in the nature of consciousness and experience. If every possible outcome exists in some branch of the multiverse, and your consciousness only follows the paths where it continues, then from your perspective, you're effectively immortal. Not because you can't die, everyone watching you will eventually see you die, but because your stream of thought never encounters its own termination. You're always in the lucky branch, always in the timeline where you barely made it through. Now that might sound appealing at first. Who wouldn't want to be the version that always survives? But think about what that actually means. It's not that you live a long, happy life, it's that you survive every single life-threatening situation, no matter how unlikely. You're always the 1 in a million case, the sole survivor. And as the improbability stacks up, you might find yourself in increasingly bizarre, isolated, or horrific situations. You survived, yes, but maybe you're the only one. Maybe you're injured. Maybe everything around you has collapsed, but somehow, against all odds, you're still here. This isn't a happy ending, it's more like a curse. If your awareness always follows the surviving path, you could end up in scenarios so statistically improbable that they verge on nightmarish. Every close call, every near-death experience, you're the one who squeaks through, and the universe you find yourself in might become stranger and stranger as a result, because you're always in the tail end of probability, the branch that almost didn't happen. From a physics standpoint, this is just one interpretation. Not all physicists accept the many worlds view, and not everyone agrees that consciousness works this way. But it's a natural consequence if you take many worlds seriously and apply it to observers. If every quantum outcome creates a new branch, and you're a quantum system like everything else, then your conscious experience must be branching too. And the only branches you can ever know are the ones where that experience continues. The quantum suicide paradox also exposes a huge gap in our understanding, the connection between physics and consciousness. We can describe particles and probabilities with incredible precision, but we have almost no idea how to incorporate subjective experience into the equations. Most interpretations of quantum mechanics try to avoid the issue altogether, treating consciousness as irrelevant or secondary. But quantum suicide forces the question front and center. What continues when everything else changes? What is it that experiences one branch and not another? There's no experimental way to test this. You can't set up a real quantum suicide device and report back from the inside, because anyone observing from the outside will just see you die in half the trials, exactly as expected. The paradox only exists from the first-person perspective, and that's a perspective science doesn't know how to measure. It's subjective, internal, inaccessible from the outside. And yet, if many worlds is correct, it's the most important perspective of all, because it's the only one you'll ever have. This thought experiment doesn't give us answers. It gives us a deeply uncomfortable question. Is the version of you reading this right now just the one that happened to make it this far? Are there countless other branches where you didn't? Where some random quantum event went differently and you're not here? And if so, what does that mean for identity, for meaning, for the choices you make? If there are infinite versions of you, and you're only aware of this one, does free will even make sense, or are you just riding along in the branch that happened to unfold this way, while countless others unfold differently? The quantum suicide paradox is disturbing because it takes the abstract weirdness of quantum mechanics and makes it personal. It's not about particles in a lab. It's about you, your awareness, your experience of being alive. And it suggests that the universe you think you're living in might not be the only one. It might not even be a likely one. It might just be the one where you happen to survive long enough to ask the question. When people hear the word paradox, they usually think of logic puzzles or brain teasers, something strange but mostly harmless. But in quantum physics, paradoxes aren't just puzzles. They point to something much deeper, a place where our understanding of reality breaks down. In classical physics, things make sense. If you throw a ball, it follows a path. If you flip a switch, the light comes on. You might not know every detail like air resistance or exact current, but the basic logic is solid. The world behaves consistently and predictably. That's how Newton's laws worked. That's how Einstein's relativity worked. Everything had cause and effect. If something happened, there was a reason. But when scientists started examining things at much smaller scales, atoms, electrons, photons, they noticed something strange. The rules didn't just get more complicated, they got fundamentally weird. It wasn't that they didn't understand all the variables. Even with complete knowledge, they couldn't predict certain outcomes. They could only calculate probabilities. That's where quantum mechanics came in. It gave us a framework to deal with unpredictability. Instead of saying this will happen, quantum mechanics says this might happen with this probability, and it works. Quantum theory is one of the most accurate scientific theories ever created. It powers electronics, lasers, MRI machines, GPS satellites. Without it, modern technology wouldn't exist. But here's the problem. Even though quantum mechanics works incredibly well in practice, we still don't really understand what it means. The equations describe what particles do, but they don't tell us what those particles are or why they behave that way. When we try to figure that out, we run into paradoxes, situations where different parts of the theory seem to contradict each other or lead to impossible conclusions. These paradoxes matter because they tell us we're missing something fundamental. It's like having a phone that works perfectly, but occasionally the screen flashes strange symbols you can't explain. Sure, it still functions, but don't you want to know why those flashes happen? That's what quantum paradoxes are. They're glitches in the story we tell ourselves about reality. One of the biggest issues is measurement. In quantum mechanics, a system can exist in many possible states simultaneously, a situation called superposition. But when we measure it, we only see one outcome. That's fine practically, but what exactly counts as measurement? A machine? A person? Does the universe know when it's being measured? That's where things get fuzzy, and that fuzziness leads to confusing scenarios. Particles that seem to choose a path only after we look. Systems that appear to depend on whether someone observes them. In some cases, the outcome of an experiment appears to depend on decisions made after the event took place. These aren't just theoretical ideas, they come from real experiments, repeated many times, and every time they make physicists uncomfortable, because the results challenge basic assumptions about time, space, and cause and effect. Even worse, there's no single interpretation of quantum mechanics everyone agrees on. Some physicists believe the wave function, the mathematical object describing a quantum system, is just a tool for calculating probabilities. Others think it represents something real. Some say particles exist in many worlds at once and split into separate realities when measured. Others believe everything is deterministic and we just don't have all the information. Still others think consciousness plays a role in collapsing possibilities into single outcomes. The giants of physics felt this discomfort keenly. Richard Feynman famously said, "Nobody understands quantum physics." Niels Bohr went further. Those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. Roger Penrose declared, "Quantum mechanics makes absolutely no sense." Einstein, unsettled by its implications, warned, "If it is correct, it signifies the end of physics as a science." And Schrödinger, whose equations fueled the revolution, lamented, "I do not like it, and I am sorry I ever had anything to do with it." These voices remind us quantum mechanics isn't just a puzzle to solve, it's a mirror reflecting the limits of our understanding, a challenge we may never fully meet. For now, we measure, we marvel, and we muddle on, caught between awe and frustration, at a universe that refuses to play by our rules. These disagreements aren't just academic. They reveal how little we really know about what's happening at nature's deepest level. Quantum paradoxes force scientists to confront that uncomfortable fact. They're like cracks in a wall. You can paint over them, but they're still there. And if you ignore them too long, the whole structure might be less solid than it seems. That's why these paradoxes keep scientists awake at night. It's not just that answers are hard to find, it's that the questions themselves shake the foundation of how we define reality. Every paradox is a reminder we're dealing with a universe that might not work the way we think. Our picture might be incomplete, or maybe we're asking the wrong questions entirely, and that's what makes them so powerful. Paradoxes are the universe's way of telling us, you're not done yet. They mark the boundaries of understanding and point to places where something new might be waiting. Some of physics' biggest breakthroughs started with paradoxes. Newton's laws came from questions about planetary motion. Relativity emerged from inconsistencies in electromagnetism. Quantum theory itself was born when classical physics couldn't explain certain phenomena. Each time the paradox wasn't a mistake, it was the key to a bigger, more accurate theory. Maybe we're standing at that edge again, approaching a new kind of physics that will explain why the quantum world looks the way it does, not just mathematically but meaningfully. We don't know what that theory will look like, but if it exists, it will have to explain why the universe behaves this way, not just how. Until then, we're left with a model that works beautifully but leaves us full of questions about reality, identity, observation, and time. Questions that science alone may not be able to answer, at least not yet. And maybe that's the most honest place to start, not with answers, but with awareness. No matter how much we've learned, we're still staring into the unknown, still chasing something just out of reach, still trying to figure out whether what we see is real or just our way of looking at it.